Okay, so the case studies that I'm going to take you through are a bridge that we did the erection stress analysis for in Bahrain. Doha metro station roof. Now you might be thinking, hold on a minute, that doesn't sound like a bridge. And you're right, it's not a bridge, but it is a steel structure and it has similar behavior to a bridge. And this one here, which was a bridge that was going to be built in Sunderland, but was unfortunately canned because of cost, we used a similar method on there when I was with Houston, so I'm going to take you through that with the solids. And then a temporary bridge for Doha Metro, some specific things that we needed to think about there. And then after that, I'll just close very briefly with some other project applications, some specific uses of the software that we have found very useful, and a couple of bits and pieces that we really like about the software that we use a lot throughout our time in the office. Okay, so the case studies: Bahrain Bridge, Doha Metro Roof, and Green Line. And starting off with the bridge. Okay, so this bridge is a steel bowstring arch bridge, but the quirky part about it is that the deck is actually concrete. It's a post-tensioned concrete deck, transversely and longitudinally, with a steel girder for the arches, and then tension, obviously, hangers for the cables. This is our relatively basic view of the model, and constructing this model was not all that complicated, really. And you'd be sat there thinking, well, actually, you could build that in pretty much any software, and the designers of the bridge did. But our remit on this was to do the erection stress analysis, consider every stage of its erection, and also to master plan the installation. Now, this was going over the main road in Bahrain near the naval base, and as a result, they couldn't build it in situ. They had to build it about 320 meters away and move it into position. So what we had to do was we had to model every single part of the system, including the casting of the deck, the erection of the arch girders, the stressing of the cables, and also the moving into position. We did that with a range of elements, tension-only elements. We used the construction stage analysis tool for staged tensioning of the hangers, and compression-only supports over the top of the falsework where the concrete was cast, and then we used the force displacement method on the supports to simulate jacking of the bridge. Okay, a couple of anomalies that occurred due to the way in which it had been modeled. One of those was peak stresses where we had point connections, but that's something that you'll all be coming across in every single piece of FEM software that you use. And there's just a sense of engineering judgment that's required on those elements. And then we got transverse bending in the longitudinal deck, and we had to take a view on that. We had to be very, very careful with the stresses that were coming out of that to determine whether they were real or not. Okay, so we used the construction stage analysis, and the following slide shows the build-up of this to calculate the pre-camber. Now, the importance of this construction stage analysis tool within MIDAS, as opposed to using other forms of software where you have to do it manually with different models, is that you actually get a true relationship and behavior of the structure as it evolves throughout the construction process, including the history and the build-up of all of the construction stage stresses. Okay, so we were able to determine that the stresses were okay, and we were also able to really get to understand the relationship between the girder and the deck, both of which were extremely flexible. So here's our model in a fairly basic sense, just a few views. The deck being cast, that was cast on compression-only supports, and then the erection of the arch. Then we had to go through a depropping sequence on the arch to make sure that we didn't have any lift-off or any overstress within the arch elements. And then we had to install the cables. It all sounds fairly straightforward, doesn't it? as soon as you get to the situation where you need to lift the deck off the casting bed, which didn't work. There was no sequence of cable stressing that we could come up with that would actually lift the deck off, and that's because the deck and the arch itself was so flexible that it would have taken 1 kilonewton in each cable over and over again, so about 4,000 stressing sequences to actually lift the deck up. So we had to think laterally. We had to think of something else. So what we decided to do was to actually lift the deck at either end using the force displacement of the supports. So we started with a nominal tension in the cables, just to make sure that they were active and straight, trying our best to simulate the real life situation. And then we took the supports and we lifted them up bit by bit. And you can see here the reactions from the compression-only supports underneath. Okay, so they're gradually reducing and reducing. And the MIDAS model predicted that we would need 90 millimeters of uplift at the supports, and we actually only needed 100, or 95, 100. So we were within about 10%, which was quite encouraging. Later on, we needed to move this bridge into position. Now there's a few photos after this and a very, very short video that explain that process. But this lifting girder at the end was also modeled in MIDAS. It's a frame model with rigid links to simulate the correct location of the connection of the various different elements. And it's stressed down to the deck. So we actually use this to lift the deck off the supports again, and then we support it on either side. Now I'm guessing that this will be a laser, so we'll try the laser. Yeah. So we then change the support condition to out here, and the SPMT, Self-Propelled Modular Trailer Company, that were assisting us with this installation, again you'll see that equipment on the next slide, they gave us a set of forces that they said would be hydraulically controlled. Okay? And we were able to assign all of those loads to these support conditions outside the lifting frame, and then those forces would effectively be transferred through the frame and into the bridge, and we could complete our erection stress analysis and make sure that we had looked after the bridge in the best way possible. So there's the actual bridge in position, and hopefully this photo now gives a little bit more context to the preceding slides. So there we have our lifting beam that you just saw sat on the self-propelled modular trailers. The concrete deck, post-tensioned in both directions, transversely and longitudinally. The arch that we needed to come up with the depropping sequence for, and the cables, which we didn't stress. Okay, we stressed them to a nominal 20 kilonewtons to make sure that they were straight and active, but they were stressed by the action of lifting the bridge. Okay, and MIDAS gave us the confidence to do that. Okay, there's another view there, working through the night, and quite a slender connection here, and with the tension rods going up through, and that's what the entire weight of the bridge was taken on, 16 of those rods. Okay, so moving on to Doha Metro. Okay, it's not a bridge, granted, but it's a fairly complex steel frame structure that probably behaves a little bit more like a bridge than it does a building. Okay, we've actually used solid elements on this particular project, and there is a reason for that. The frame is very complicated, and in some locations we have to have full moment connections with maybe 5 or 6 members coming into one connection. So there's 2 reasons why we've used solids. One of them is so that we can take direct stress output for use in the design and to justify the structural capacity of the connection. And the other is to satisfy ourselves that if we can build the section, that connection in solids, then the fabricator will also be able to build that section in steel plates when it comes to it. Because it's very easy, as you know, to put a whole load of lines to a node within a model, and then MIDAS will give you a great rendered image of this model, and it looks fabulous, but if nobody can build it, then it's not so good. So those are the 2 reasons we did it. I'll take you through a few images first to give you some context, and then I'd like just to take you through very briefly the method in which we incorporated the solids into the frame model. Okay. So Doha Metro is quite an extensive, brand new metro. There's no rail in Doha at all at the moment. This is just a few diagrams to give you an idea of the scale. Doha itself is not the biggest place in the world, but they're being quite ambitious with their metro plans. And there are 2 major stations. There are obviously hundreds of stations over the network, but there are 2 major stations that have significant structures above ground. This is one of them. This is Musharraf Station, to give you an idea of scale. The roof, the part of the roof on the left there, up here, is about 15 or 16 meters up in the air. So it's the height of a 2 or 3 story, well, 3 or 4 story building. So it's not small. And these shapes here are going to be clad in natural stone, and within that there needs to be a steel frame to support the spans of up to 30 to 60 meters, depending on where you are within the structure. So this is our steel frame in green underneath this kind of translucent shell. And this is another station, Education City. This is the second of the 2 stations, which for the last 10 months has been mothballed, but actually is coming back. This one presents an enormous challenge. The construction depth along these ridges is only 800 millimeters. The span is in the order of 30 meters. And the cladding supplier wants a 400 mil cladding zone top and bottom. 100 mil construction depth. You'll be wondering how the hell that's possible. I'm sure time will tell. Anyway, this one's only now being resurrected. So yes, steel frame with complex geometry. We were very keen to have the correct connection relationships, so the model has a number of offsets with rigid links. Rather than using the offset tool with respect to the section geometry, we went for a center-top relationship so that everything was lined in, and then offset the connections where we needed to using rigid links. We also played around with the temporary support conditions, so we used a little bit of construction stage analysis with this roof, because we wanted to pin the supports for some of the modules during construction, because the dead loads induced quite significant bending moments. So if we could take out those bending moments by manipulating the geometry and the support condition, then we would save ourselves some material later on. Okay, so it's a standard 3D frame in MIDAS with normal beam elements, generally speaking, a few links that I've mentioned, and then the complex connections we wanted to do in solids, so we used another part of the MIDAS family called FEA. I don't know whether any of you have come across FEA. It has a slightly different user interface to MIDAS Civil. I'll be honest, it's not quite user-friendly, but as with any item of software, once you actually get into it and use it, it's no harder to use than anything else. But it's phenomenally powerful. And I'll touch on how powerful later on with some of the other kind of short-term examples. Okay, so I'm just now going to take you through the steps that we used to incorporate solids into the frame model. If you have any questions on that, by all means, shout out. So we would start with our frame, and we would identify one of our complex connections. We take this one. This is just an example. And we would divide the incoming members to that connection in such a way that the closest members to the node would finish outside of the fabricated connection. Okay, so accounting for all overlaps within the system and all that kind of thing, we can set them outside. We would then extract that node with its connecting elements, just this length here and this length here and so on. We would extract that and we would export it to DXF. Now, I don't know how many of you in the room use MIDAS or have used MIDAS, but the export DXF tool is incredibly powerful. Okay, even in the frame situation, it will export or give you the choice to export the shape and the center line and the thickness, okay, or combinations thereof. Now, if you export the thickness of this, you get this box section, this eye section, with the correct flanges, the correct webs, in the correct geometry, with the correct center lines. And that's amazingly powerful for you to then be able to take and manipulate. Whether you just do that for the whole frame, pop it into a rendering package and make it look like a fabulous structure within 5 minutes of having started the model, that's great, and it's a quick win with your client. Or whether you use it as in the way that we're just about to. So we take that, we export it by DXF, and we put it into AutoCAD. We then use the local coordinate system within AutoCAD to draw a set of rectangles at the end of each of these elements. And then any connection plates that we might want, we would insert at that point. So if we wanted to sever the joint between this box here, that you can just about see coming out in this direction, and this one over here, we might want a plate that ran through the middle so that we could make that connection in real life. Okay? And if we wanted to do that, we would insert that plate just as a rectangle into AutoCAD using the functionality of the local coordinate system. Once we'd done that, we would then have a rationalized set of geometric data. We would have a series of rectangles or lines on the faces of the elements that we wanted to connect. We would have their center lines still from the MIDAS model, from the MIDAS output, and we would also have any connection plates that we wanted to add in as well. I would add that you could do all of that in FEA directly if you wanted to. You could just take the DXF output, pop it straight into FEA, no problem. We find it a little bit easier to play with in AutoCAD and add in that step. Once we're in FEA, we can then create a series of surfaces from that line data that we have rationalized and effectively extracted from the MIDAS civil model. Okay? And being very, very careful, and I'll go on to a few kind of top tips for solid modeling in just a moment, but being careful, we would ultimately extrude those surfaces to create the three-dimensional shapes. We would then subtract and fuse using the Boolean commands within MIDAS FEA to actually give ourselves a single entity volume within FEA that we could then mesh. Okay. Now, there are a few do's and don'ts. If you're going to do a lot of these types of connections on a particular project, then it's important to spend a fair amount of time at the beginning establishing a routine for how you go about it. And once you've established that routine and it works, don't deviate from it. Because you'll be there for a week trying to work out what went wrong with one of them. All right? But if you're methodical and careful and you don't try and cut any corners, you'll be absolutely fine first time. When you have a solid that works, okay, and by works I mean you want to avoid, if your fusing and your subtractions don't work, then you'll have something called a non-manifold volume. And the program will tell you that you've got that, and then you just undo and you work out what it was that wasn't quite right. Now sometimes that's because you've got a very, very narrow discontinuity. If you're trying to fuse two plates and you're expecting their surfaces to be exactly flush, but if you're, say, 0.001 of a millimeter out on one of them, then it may not like it very much. But once you've got your solid, then you can mesh it using the auto mesh. The auto mesh tool, very powerful, lots of functionality. You're all engineers. You know what kind of sizes of mesh you should be looking at. To give you an idea, this one here, we typically set the mesh size to about the same thickness as the plate. Obviously, the results will be more refined if we went for a smaller mesh size. But to give you some idea of scale, there's about 100,000 elements in this particular unit. So you insert that into a frame model, and your civil model is going to be working quite hard. So you can't go crazy. But what MIDAS FEA will let you do is it will let you control the element size along an edge. It's called mesh size control, and it's a very easy tool to use. Once you've done that, you can then export it using the MCT command within MIDAS and import it back into your MIDAS frame model. Okay? And all of this can be done provided you stay in the same geospatial coordinates. So you export from MIDAS Civil into AutoCAD in the same coordinates, into FEA in the same coordinates, and then back from FEA into Civil in the same coordinates. And all you have to do then is use the rigid link command to connect your connection into your frame model center lines. Simple, yeah? Dead easy. And it really is. I mean, it's complicated the first time you do it, but trust me, if you get into the routine, you know what to look for, you don't fall into the traps, it's fine. We find it incredibly powerful for overcoming very complex connections where you really want to be sure that you're not overstressing some of that part of the connection, and you want to avoid the complexity of trying to establish the correct boundary condition. Because of course you could analyze this within FEA, and FEA is fabulous at analyzing things. But you'd have to generate exactly the right stiffness of boundary condition on each of these corners, or each of the faces. The other thing I would add at this stage as well is that if you do have complex shapes but you don't fancy going all the way to FEA, I understand that MIDAS now do, is it FX or FX Plus? Ask one of the MIDAS guys, which is a meshing tool. It doesn't do the analysis, but it will help you to mesh very complex shapes. Okay, so just to, when you're transferring it back, you just need to be careful that your MCT file is going to be compatible. MCT is, for those that don't know, is MIDAS's command shell, they call it. It basically allows you to take syntax data from one model and import it into another. Okay, it's also a very powerful tool if you want to generate that syntax within, say, Excel. You can automatically generate the syntax and import it, which is very useful for tendon data, for post-tension bridges. Okay, so provided you keep the same coordinate system, you're absolutely fine. A couple of solid modeling tips then. Follow the same convention each time. I've mentioned that. Don't rush, don't cut corners. Label your objects within FEA very clearly so you know what you're working with. And most importantly, if you're trying to, say, make something as simple as an eye girder, let's say, within FEA, make sure that your web overlaps halfway into your flange, top and bottom, so that when you fuse, you know you're fusing right the way into the section. Now, obviously, afterwards, it doesn't double count that little bit of section, but it means that instead of trying to go edge to edge, where you run the risk of having an infinitesimally small bit missing, which will give you this kind of non-manifold shape and it won't mesh, it avoids all of those kinds of things. So try and overlap things a little bit. Same goes for subtraction. So if you're looking to subtract from an object that you then want to fuse to another, you subtract a little bit less than you need to, or you want to, so that it fuses correctly and you have that overlap. And then when you come to a complicated shape like as we had a moment ago, when you come to fuse it at the end, you do it progressively. You don't try and fuse them all together, because the fusing engine will just give up. Okay, it won't know what to fuse in what order, and then it will get hung up on trying to fuse things that won't fuse together. If you do it progressively with the overlaps, you'll be absolutely fine. Okay, so moving on. This is a great system, by the way. I can thoroughly recommend, if you're ever doing a presentation, have the timer in the top corner. Right, a tunnel boring machine bridge. Not many bridges carry tunnel boring machines. And to be fair, this one was fully supported on the ground when the tunnel boring machine went over it, so I can't claim that it spanned with the machine on top. But what we were asked to do was provide a temporary bridge where the tunnel boring machine could go across, and then they could excavate out underneath the bridge with what they call a multi-service vehicle, or an MSV, running over the top, bit in the middle of it, slightly lower down. Okay? So we had two models for this. We had a line model and a plate model. We built a grillage line model primarily so that we could design certain elements of the structure, primary longitudinally spanning elements of the structure, in a conventional codified way, because that's what the client wanted to see. And you'll see from the shape of the box girder that it would have been pretty tricky to do that in a codified way had we not had the grillage. So we had a rudimentary grillage, and then we used the plate model to verify the deflection criteria and to confirm the behavior of the bridge. So that's what we've just been through. This is the cross section. So here you have the bottom line of the tunnel boring machine, and in the bottom here you have where they wanted the MSV to be able to drive afterwards. And so that line there was our top profile. They then welded 50mm rails on here for this tunnel boring machine. The boring machine itself is not actually that big. It's only about 7 meters in diameter, which is, by tunnel boring machine standards, is fairly mid-range, I would say, I think. So this is our rudimentary grillage model. We split it into eye sections with the box and with the transverse elements underneath. And that was so that we could effectively design each of these eye sections and determine what proportion of the load each of those primary load carrying members was taking. And then this was the plate model that was built up after that. And what I've tried to do here is take a bit of a section through by deleting some of the elements so that you can see the inclined stiffeners that we had in there that were there to take the MSV wheel loads, the inclined stiffener in the top. There was a plate that ran through at this level to tie the whole thing together. And the plate model itself gave a very reliable stiffness profile and deflection results. And the other reason that we needed to do the plate model was because we had splices at third points, but we didn't, because of the requirements for the TBM to go over the cross, over the top, we didn't want to interfere with the top flange on this inclined plate. Plus the access was a nightmare, so we decided we wouldn't have any bolts on the top flange. And you're saying, well, how did you do a splice at third points without bolts in the top flange? Well, we only put bolts in the bottom flange, and we had bearing plates in the top flange because it was a simply supported bridge. We knew they'd always be in compression. So we were able to play around with the engineering a little bit to try and make it a bit easier for the contractor. And all of those connections, and you'll see this on a stress plot in a moment, were modelled within MIDAS Civil with compression-only links. And there you can see those stress concentrations that occur at those bearing points where the splices were. So we were then able to make sure that we had the correct stress output for the design of those bearing calculations. And there's the bridge on its concrete support, back blinded for the tunnel boring machine to go across. Unfortunately, I don't have a picture in the presentation with the tunnel boring machine on there. There you can see the profile that you just saw on the plate model. I'd hope you would agree that the final view of the bridge looks quite close to the plate model that you just saw. And that's it. Once they'd excavated out underneath, they had a little ramp coming down onto the bottom running surface and back up again. And there you can see the cab of one of the MSVs with the concrete segments on the back of the trolley. So that's about a 36-meter span. The bottom part of the box girder was only 600 mil deep. The whole depth was around about 1.4 meters, something like that. So we were pushing the L over 20, the span over 20 limits that you normally associate with that kind of bridge and that kind of span. But deflection was not a criteria for the MSV. They were quite happy with it deflecting. It was only during the tunnel boring machine going across that the controls were quite tight. Okay, so those are the three case studies. Quite a variety of applications, various different types of elements in MIDAS. Throughout all of those, we used construction stages at least once, obviously significantly in the Bahrain example. Rigid links, elastic links, interface elements we have used. I haven't got an example of the interface elements with me, but we've used interface elements within FEA to model ground-bearing slabs. And the interface element side of things is something that's a fabulous tool, because how do you model the relationship between two different materials when they're not mechanically connected? So to be able to have an infinitesimally thin layer, if you like, within your model, where you can give that layer a behavior, it's a very, very powerful tool for some of the more unusual analyses. Now, I'm just going to throw in a few other project examples. We get involved a lot when things go wrong. And the Middle East being the Middle East, things go wrong a lot. So we make a good living out of people making mistakes. I've put use of embedded tendons. That's not the case on this next slide. So that was a bit of an error in my presentation. All three of these are related to projects where we were asked to come in and investigate what had happened. On one of them, on this first one, the contractor had stressed the tendons and a number of the joints within the segments of this post-tension concrete bridge. He had bursting of the concrete. It actually just exploded during stressing of the tendons. Now what we found out was that the tendons had floated during the casting process, and you ended up with a tendon profile or a duct profile that looked something like that. and as a result there were localized pressure points which exploded in the concrete. Now, as part of our investigation, we embarked on a solid model within FEA again. We were able to model the duct line perfectly within the solid and extract and subtract that using the Boolean commands, and then we were able to mesh that solid to give us the concrete with the duct in. And then, just using a hand calculation and manual application of load, we could apply the radial forces from the tendon to determine whether we had any localized stresses that would give us or indicate that we would get bursting or cracking, splitting of the concrete, which we did. And this was one of the stress plots that came out of that. On another bridge, and I can't tell you which one, but those of you that have lived in Dubai might recognize this, we were asked to investigate why there were a series of diagonal cracks between blisters. And so as a result, we actually built this model, again, completely in solids, including the blisters, which you can see there. Horrendously complex geometry. This was a real eye-opener and a real learning curve in terms of modeling solids and following the rules that I was talking about earlier. It's unfortunate you can't see the other side, but there's another surface that's cut out of the bridge, concave, varying depth surface on the other side. But anyway, the whole thing was modeled in FEA in solids, and we used embedded tendons, which is another function within MIDAS. Okay, you can just about see those different colorations on the faces of the blisters, and that's where the tendons terminate. So that's where you get your stress concentration in the blister block. And you can see here these areas of orange in there indicate a tensile stress between the two blisters. So because of the proximity of the blisters to one another, top and bottom, we were able to determine that they were effectively trying to pull the bridge apart in those locations, and that was not a factor that had been considered in the original design or the original reinforcement layout. So if any of you have particularly shallow bridges at the moment that you're designing with opposing blisters top and bottom, I urge you to consider this in your design, or by all means model it in FEA solids with embedded tendons and see whether you have a problem. And here's a classic one. Another job in Dubai. Again, I can't tell you which one. I don't know whether Mr. Choi can recognize this. Maybe. But yeah, this one, from an engineering perspective, and what really happens in real life with bridges, I think this failure is absolutely fascinating. If you want to know why, by all means, collar me afterwards. But be prepared for a long-winded explanation. But essentially this had happened because the people involved in the design one person had done the track structure interaction to find out what the forces were on the substructure, and one had done the track structure interaction to find out what the stresses were within the rail. Now, once they'd done the rail analysis, they determined that they needed to move the movement joint in the rail. So they moved the movement joint to a position that was immediately over a pier that was fixed in both directions for the opposing spans. So they had a rail on top that was free to move, and they had two sets of bearings underneath that were not. And basically on an uncharacteristically cold and wet Dubai night in February a couple of years ago, the two bits of track either side of this pier decided they were going to pull the bridge apart, and they pulled the shear key off of its plinth, or out of its plinth, and this crack actually extends down into the middle of the pier. So basically from that, we were asked to get involved as an independent third party. Obviously the three design teams were well on the case, and we came in and basically just corroborated what they'd already found. But we did find that the MIDAS track structure interaction tool was incredibly quick and easy to use. We'd done track structure interaction analysis before. We'd even done it before using MIDAS without the wizard. But using the wizard is incredibly fast in terms of setting up all of the different nodes that you need with your horizontal springs and what have you. So it's just a useful tool there that we put to good use. And finally, just wanted to touch on some useful features that we use. The structural wizards, you saw in the videos of the many people giving testimonies before the seminar started, that they were praising the structural wizards, and they are very, very powerful, particularly for things that are more complicated to engineer, such as the geometry of suspension cables, geometry of and setup of cable-stayed bridges. Yes, you're going to have to manipulate the model afterwards. It's not the finished article, but it certainly saves you a couple of days' work in getting to that point. The rendering and DXF capability, we've already touched upon that with the solid element modeling. But if you're working for a client who's very keen to see what their structure looks like, you model this in MIDAS, or you model that structure in MIDAS, and before the end of the day, you're able to give them a rendered image of their structure, which is a quick win. It's a, hello, Mr. Client, please see how far we've got today, and he thinks that you're amazing. He doesn't know it only took you 5 minutes. And then construction stage analysis. It's not just about construction stages. We've actually used construction stage analysis in the past to be able to run analyses that vary the geometric and the material stiffness of a structure. So we would force the displacement of the structure and at the same time have an E value that varied with time so that we could simulate the variation in the material for that structure. So you can use the construction stage analysis tool quite differently and innovatively to do things that are otherwise, frankly, not commonly possible. I'm sure that there are many other things. The MCT command shell is fabulous as well. We have spreadsheets that for precast segmental bridges, for example, where we just have to enter the tendon data from the contract drawings, and it will generate the syntax for the tendon layouts within MIDAS. Simple. And you can do that because of how easy it is to generate the codified syntax that you can then import through the MCT. Thank you very much for your time.